Hi, everyone. Thanks a lot for being with us in such good weather. I'm Oleg Bonder, and we work together with Alexei Dmitriev in Yandex, and we develop our database in Yandex DB, and the amount of data is growing fast, and there are a lot of difficulties around that, and we want to make sure that the database would have everything, and we have to build the security platforms, and we will show how these tasks influence our development, and then when we tackle these issues, how much easier building such systems becomes. And we will talk about both parts. I will talk about our platform, and Alexei will talk about how we built our platform on YDB. Let's start with the very beginning. So what is YDB? It is a database that we did in Yandex, which is scalable and really productive and really robust. And one of our main tasks is to survive different catastrophes and to work with a lot of data. It should be fault-tolerant and versatile. When we started the development, we wanted to build the transactional and traditional database because by then there was this famous scientific article, and the trend started about the evolutionary database, and then the new term was introduced for a hybrid transactional analytical databases. It all started with the database that should work in one memory, and then Gartner said it could be one database, and you can keep the data for transactions and for analytics, but anyways, it will transfer the data internally, and closer to 2020, this class of the databases became more distributed. At first, they were columnar type, and then they became more distributed because no server can keep all of the data because it can be hundreds of petabytes. We started the development, and we understood that we cannot do just that transaction, and and when we became popular as the transactional system for data management, on the one hand, every project we had, they wanted to create the base for the tactical tasks, and every team also wanted to have another database for logs, and the number of logs increased, and the tracing became the thing. And one of the areas that we worked on, apart from the relational system for database management, we also had to tackle the databases for the logs, and this is quite problematic because the log usually is sorted time-wise, and all the data goes into the last set of keys. And when there are too many logs doing the search in the transactional database, which is used for both purposes, becomes difficult, and we had to come up with a full analytical engine because a lot of the security platforms, they are complementary to all of those issues, and we had to address all of those. When we talk about hybrid databases, there are four key difficulties, four key challenges that you have to tackle. And number one is how this data should be kept. Why can't we use just one system? Most likely, the workload can really vary. In analytics, there is a small number of queries, but it can need a lot of other data. And we have to think about how we should store that optimally. It means both columnar and row storage. And we want to get access fast to the data that we have there in analytical storage of this database. So we have to transfer the data from the columnar database from the row base to the columnar base, and we want to do that inside the system without anything external. After we transfer this data, we address the issues of data freshness. We have to ensure the queries for each of those subsystems, and we somehow have to learn to isolate the resources. And today I want to cover in brief what functional features we had to add to tackle the issues. First, I will cover what the system looks like. It is broken down into layers, and one of the key features is decoupling. So the layer of computing is separated from the layer of storage. This can be done logically on ordinary servers. Some processes only do computing, and all the data is stored in the storage layer, which ensures that any layer can be scaled up so easily. The database can keep a lot of data, but the number of queries is small. Or the other way around, 1 million queries per second can be sent to a small database. And then you have to split it into different layers. The query processor working with the user ones, and then the layer called tablets. They are small logical programs, and that's what you can call them, which actually work with the data in different formats. And it could be the program that works with the data of the topic. And under the hood, there is the data, and each program has its own data, and it talks to the layer of distributed storage, and through put, get, patch, delete, it works properly, and the storage layer ensures that all the redundant copies are kept kept in storage. And what we had to do additionally, initially we built the system on tables, which is a primitive thing to do for any database. We have the tables, and a table has a mandatory primary key, and the primary key is also the key for the system. So the system collects the data for the collected data and the queries, and when the workload increases, the system itself makes a decision that the spreadsheet should be broken into chunks. And the hardest thing is not sharding. You can do it once and easily, but when the nature of turning to data is changing, then we have to do a new split up. This is done automatically based on statistics. When we understand we have less data or less workload, what we do, we merge the adjacent shards so that we rebalance and adapt to them. Inbound workload. For analytical workload, this wasn't enough. We had to add a different way of sharding based on a hash, on a key, because here in a massively parallel system, we want to be able to use all the computing resources. So we split all the sharding throughout the hash, and we spread this throughout the cluster. So when the query comes to the system, it is sold to all the areas, to all the nodes, and we can then work in parallel. So if we have to increase the amount of handled data, automatically the shards are distributed throughout the cluster and the productivity increases. Since we had quite a lot of time to work with the logs, when we were a single system for log storage, we wanted to somehow cap the growth of the size of the spreadsheets, because anyways, even when there is a timestamp, we have the overheated shards. What we did was we split the data by projects, and since there is something similar to a filing system, we created we broke this into projects, further than into stages, hosts, and pods. You can build a certain hierarchy, and then the data is kept in this hierarchy. But the volumes of projects became so huge that this wasn't enough. But anyways, we believe we have quite a practical approach. There can be a million different tables, and creating every time a table and keep a metadata when there is a million times more volume. This is not enough. And we also want to redefine the qualities of downloading the data and uploading. So we understood that we had to do a column store, which is the scheme that has the tables that are one logical chunk. And for similar logs, now we create this through logs and to change all the tables, you change the log store, not millions of tables. And there can be a lot of data in the tables, and the system is distributed, and the shards are on different hosts, and to do the final calculation on the node, we could flood the whole thing. We push down all the calculations as much as we can. They can be built as simple arithmetic operations or some preset the functions, everything towards not just minimizing the reading of these disks, but also transferring data. And the next issue is about the data freshness and data transfer. And we had a solution for replacing Kafka, which we are already using in Yandex. And in the same database, we can create topics and use them as the replacement, a substitute for Kafka. And this is FIFO sequence, which can be split just as the table by parts. And to transform the data from one shape to another, we want to avoid external tools. We understood that we could take the topics and use them for the transfer, but not to write any additional apps. We implemented this through a transfer, which enables us to configure the tables and transfer data between different things. It could be transferring data between the columnar and row tables and do some operations on them. And since we want to continue working in the system with the consistent data, we also added the transaction support. And this is why we wanted to have the support of transactions between the topics and tables. You can read data from the topic, and then you can write it in the table, and then retrieve it through one line of code. And we also had to work on the optimizer. And in the basic system, we had quite a simple optimizer, which was enough for us. It was built on the basic set of heuristics that we have accumulated over the years of usage, and to make sure that changes in the code doesn't result in destructive regressions. We have the collection of queries, explain planes, and statistics, and we run this through the so-called query checker, and we run the sample of queries on these new rules to make sure that we do not fail. But this is not enough for analytics. So over the past few years, we had to develop the cost optimizers that is based on the statistics and information that we get from the tables, the size of the tables, the number of rows, and when we keep data column-wise, we we do not have enough. We have to collect the sketches of data about how much volume do that data take. And here we use modern algorithms. The algorithms based on buffs, and we look at all the possible options to identify on a lot of joins in the query. It can be up to 100 joins, and how we can optimally transfer the data throughout the network. With all of this experience of building the systems and storing data, we built a versatile solution, and now we want to show to you how this works and what we have done with this. Hi, everyone. My name is Alexey Dmitriev. In YDB, I am responsible for the stream data processing. What is CM? Is security information event management system. It gets a lot of data from different sources, and then among all the data, it tries to understand if everything is going fine. If a person is trying to log in their laptop, but the laptop is closed and the person left their workplace, something is probably wrong. So this is how the system works. To make sure that the operators get the information that we have an incident in the system and the response is needed. So 3 years ago, we were approached by people from Yandex Cloud. They want to develop their own system of Yandex Cloud, and at the start, it should handle 600,000 events per sec, and it should increase exponentially because the cloud is growing. All the data that is transferred should be stored for 3 years because there is compliance and regulators' requirements and common sense. Everything that happened, we have to keep. And in 3 years, as you understand, there is a lot of data. Not only should you keep this data, but the security experts should be able to work with this and look for something. But the most complicated thing is not that you have to store this data, but the people in the cloud are really concerned about security, and they believe the time for identifying the incident should be in seconds. The traditional systems that work with security, usually they get their volume of information, somehow accumulate that inside the system, and then every 10-15 minutes, they try to understand if there were any issues there. And so the response time is at least 10 to 15 minutes, which made them unhappy. And you can only handle that with a stream processing. You process the data in the real-time mode, and you make an immediate decision if everything is fine. So there are no delays, and this streaming approach is good. Apache Flink, Spark, Apache Beam, there are a lot of those which can process data as a stream, and to make the systems easier to use, they offer the syntaxes to make it easier. And this is similar to the traditional query. There is a filter, and the only difference is that in green you see the special stream commands that can result in certain results, but everyone who has written anything in SQL is used to that. And at the end of the day, how they wanted to see the CM of Yandex Cloud. At first, there are sources of data, then there is the note of normalization. Normalization is an answer between what is similar between the laptop and, for example, the door sensor. They both have an IP, so they all have IP addresses, and normalization is that you are taking the input data, inbound data, and if in the data there is an IP address, if there is data about the login, it gets into the login column. So the analysts know exactly where to look for data. If it is a laptop, I don't have to think that it is an IP form. I can always look it up, and that makes the data usable. The second thing is keeping data in the logic storage. With a lot of data, we want to normalize the data, which means we are changing the data, and something that seems unimportant is cut off, but this data may be important. And when there is an investigation, we want to get maximum data. Or why do we keep the data in logic storage? Because the logic storage is the cheapest way to keep a lot of data. And the object storage. And then we want to make sure that analysts can find something there. All the data should be kept in the analytical database so that an analyst could get the information. It could be incidents, a response, or building other solutions. And the final thing that we have is sending all of those normalized data into the module of streaming, which works on identifying the incidents. And now let's talk about why Yandex Cloud and YDB are connected. I will give you a few numbers. Back in 2015, the YDB team was approached by the search portal. You all entered Yandex, and everyone sees a different start page. Yandex adapts this page for you, and this portal wants to make sure that this adaptation would happen really fast. Once you do anything, it should be reflected in the start page. And the search portal should be adapted for your activities. And in YDB, we started doing this. And right now, it handles 80 gigabytes per second so that everyone has a Yandex of their own. When the guys approached us, they knew we had that, and they came to us with the numbers. It's 20 gigabytes of data per second. That's raw data they were getting at that time from all sources. After normalization, we have the flow of 600 megabytes per second, and with this we have to identify if anything goes wrong. There are 120 rules for correlation to identify incidents, and it's still growing. And when we do normalization, like I said, we are trying to find some specific attributes, and now we have over 1,500 unique properties of data that we are using. And then it turned out that this whole system can be broken into three components. So the first one is object storage, because you cannot store data cheaper than that, than the CM, and it ensures all the processes.
Well, then it turned out that all this processing that SIEM needs is already there. So the module of stream processing is the first thing. It has all the data that we need, and it also operates with the correlation rules. So when we thought about how to put it together, we had different variants. First, we wanted to create our own language that our security guys will write in. But then we kept thinking about it and understood that, yes, we can invent yet another SQL language, but there is standard COE 2016. And people already thought about that. And there is the complex event processing, and inside there is match recognize command, so which allows you, by using standard SQL, to describe very difficult patterns, complex rather patterns, like stock quotes, security events, and so on and so forth. So we decided to take that in order to decrease the time we would need for learning all that. When we try to see the amount of data, we have 600 megabytes, right, and several hundred rules of correlations. So 600 megabytes into each query will give us 120 gigabytes per second. And if we're going to scale, then we'll have a terabyte per second. This will be, we will become the largest streaming system in Russia, maybe not only in Russia. We didn't want to do that. Our task was different. So we started thinking how to actually decrease the amount of data that we transmit. And it looks like most rules of correlation do not need all the data. These rules do some kind of filtration and only keep the flow which they need. So we decided to automatize the filter use. So when the guys give us a query, they understand which data they need. So we go into filters, and as a result, the correlation rules only give us the data which we need. So right now we do not use more than 1.1 gigabyte per second, which is much more than what we could have used otherwise. So when we transmit data over the flow module, it's important to see which data it is. If we see that the user Ivanov is using right now server number 1, if this is his personal server and he's working on it, that's good. But maybe it's a production critical server, and he shouldn't be there. So in order to understand what server 1 is, we use the specific component which is called lookup. So the flow system consult these lookups in order to understand what they are dealing with. When we launched the system, we understood that each second we are performing 50,000 queries towards lookups. First, we didn't know which system to use, but then we remember there is a prod system in YDB which actually can give you 1 million queries per second. And unexpectedly, we also saw that as it found out, the data has to be renewed transactionally, not only in the lookup. We haven't thought of that in the beginning, and we had some problems because there was a massive pressure on the catalogs and on the lookups. So this transactional renewal of data allowed us to avoid a lot of incidents. In order to understand how the flow systems work, there is a specific data bus line that is given to specific flow. We've had this data since 2015. We crossed them over, and it works well. The analytical database is needed so that SOC guys could consult this data in order to look for everything that they need. And on the one hand, it was important here that ADV can scale itself horizontally, because if we take 6,000 megabytes per second and multiply by 3 years, we'll have a lot of data. And the second part is it's important to work with a large number of columns. Just as all databases, initially we work with 100 and 200 columns. But when we normalize the data across all the sources, it turned out that we need 1,500 columns at the get-go, and preferably we should have 5,000, which became part of a problem because a lot of sources do not renew, do not update the data. Fire alarm, right? For instance, fire alarm maybe works only once a year, and there is, on the other hand, login and logout, which happens on a daily basis. So knowing that we have an event that is called fire alarm, and it takes more space than the data about the fire alarm. And we had to do a lot of optimization in order to learn how to work with such a great number of columns. Another thing, streaming without analytics is throwing your money to the wind. Why? Because the flow processing of data is about what's happening in the moment, here and now. You are writing a query in order to understand whether the sensors work, whether the users are happy. When you work with this data, you only see what's going on in the present moment. And it can happen that some data you are only getting once a year because this specific server is turned on once a year. It's turned on, it transmits its data, it's turned off, and you're not ready for that, okay? So the ability to store data in the analytical database and use it for our correlation rules is very, very helpful. We will then be sure that everything works well throughout the year. This is a great function that helps us avoiding mistakes. And even if query doesn't work, you can always get back to the analytical database, have more tests, make sure that everything works well, and continue. The system of data storage has to be not only efficient, it has to be cheap, because if the database is quick, but if it costs like a space rocket, it will probably be changed. So one of the requirements that we had was the push data into object storage that had to be transparent of the SOC for SOC analysts. They don't want to know where the data is. They want to send a query, get the results. That's it. And we're doing it with this transparent push into the cold data. The analysts notice that in some cases the data processing happens slower because sometimes you have to go to further removed DWH. The federated queues is something that we did not originally could make sense of. It's a federated query is a query that you can get with into any database. When the analysts started working with data, they realized that normalization doesn't always happen the way they want, or they wanted to get deeper, dig deeper in case of incidents. So they had to have an opportunity to get into the raw storage. So federated queries give them just that opportunity. Without leaving YDB, they can send their query and get everything that they need. So basically, this is where I wanted to stop. And as a conclusion, I will say, in order to launch SIEM YDB, you have to have a lot of data, databases, federated queries, and so on and so forth. All of these components already were in IDV. IDB is a system in in the making, so we are developing it all the time. My colleague told you about that, and that's what allows us to build, to construct such complex systems. Thank you very much. I'll be happy to answer any questions if you have them. Okay.
Говори.
Okay, go ahead.
Не слышно.
Как-то не очень.
No sound, huh? There is no sound.
Попробуйте выключить,
Да.
включить.
Try to turn off and turn on
Нет.
the mic. No.
Сейчас подожди. Дадим
Okay.
шанс.
Give me just a second. Let's give Dmitry a chance.
Два вопроса. Первый, собственно, Павел Велихов. Да,
Okay, I've got two questions.
Он говорит, что
Pavel
сейчас
Velihov
последние пейперы говорят, что join reordering не
tells us that
когда в продакшн.
the latest research tells us that joint reordering is not needed. Yeah, you can just do it. Send it to the production. Well, this is a difficult issue because there is some research about
Когда мы говорим про большие аналитические системы, там зачастую
about it, but okay, well, when we talk about large-scale analytical systems, we may have a large number of joins. And if we have to go through all of the tables and these joins, the numbers go ballistic. For 20 tables, there are about 400 billion of different variants. So everybody is looking for an algorithm in order not to go and sift through all of that. We are using one of the modern algorithms called DP-Hider. It's an optimizer which works on hypergraphs, and I think it's the 2017 model. There are two schools of thoughts about it. One of them says that these joins graphs can be simplified, and if you can basically streamline that into a line of strings, you can very quickly process that. The second school of thought says that indeed joins are not needed, are not necessary, but we still believe that the planning should be there, and we see that this is a good way to efficiently work with them. But when do we send it to the production? That was the main question. Okay, no, I understood.
Ты спросил, когда в прод. Этим же
When does it go to the production? This summer. It'll go into production this summer. And it's important to note, I think, that these schools of thoughts that we've mentioned, they change all the time. Different research comes out. We analyze latest research all the time in order to see how to optimize what we've done. So we keep working on it. Pavel Velihov and his team are working on optimizing that. Okay, another question. Why is your columnar format of storage better than Parquet? And what inspired you to create it? I don't think we can say what's better and what's worse than why Parquet is no good. But Parquet is being kind of scaled down. Well, we have some computation in the memory. We don't want to convert them into the disk memory. Okay, so we have our own format. At the same time, we can go to Parquet. We'll read data from it, but we'll lose some power. No, I mean internal format. It doesn't look like anything like Parquet. No, it does not. It's our own. Because what we want to kind of save money on conversion.
Первый вопрос это про стриминговый сервис, да, то есть.
My first question is about the streaming service.
Сейчас. Сделали много разных таблиц, а сделали все в одну.
Why haven't you done many tables, but rather just did one and then have to kind of to press it down? Yes, we've discussed this. One of the options that we were thinking about is when events are going into the topics, and then
Очень сложно менеджер,
we read all of
там
them.
возникает
But this is very
огромное
hard to
количество
manage
источников.
because we have hundreds, if not thousands, of sources like that. And the SIEM guys said, no, let's just have one source. It will be easier for us to tap into that, and we will distribute the correlations rules. The second question is about the rules that SIEM formulates. Is this implemented in transfer mechanisms or somewhere in an outside system?
Мы не используем внешние системы.
Everything is implemented inside. We don't use outside systems.
Мы пытались
Why
увеличить
it was
количество
important?
запчастей, которые
Well,
как-то взаимодействуют, что-то куда-то
We tried to
вот, за счет того, что все в одной базе,
decrease the number of spare parts. Since everything is in the same database, we can optimize the flows.
да.
What about the rules? The rules are also inside the database? Yeah.
Здравствуйте.
Oh, thank you.
Ну, по традиции два
Hello.
маленьких вопроса.
Traditionally, two small
Есть
questions.
набор средств и хранение стриминга, аналитические, транзакционные, колоночные, срочные у вас есть внутри.
You have all the set of means to control the streaming, and if we use yours, do we have to buy additional licenses?
Помимо
Do you mean if we take your things, do we have to buy any additional
И вообще, насколько
products? Yeah, if it's needed, or do you have kind of everything on board? And in YBD. Yes, everything is on board. Everything that we mentioned today. The SIEM system that Alexei referred to, it's all based on one product. We don't use any additional systems.
То есть мы там, например, Kafka совместим.
At the same time, we have open interfaces. We are compatible with Kafka, for instance.
самих данных, часть
And the
в облаке, часть он-прем.
and the data storage, some of it is in the cloud, others is so how is this done? There are a lot of changes that have been introduced lately. IPM or cloud, yeah, so how does this work? If you want to develop a system, well, first of all, you have to understand where the safety perimeter within which the system can live. Right? You can have two-legged structure, one in the cloud, the others elsewhere, but there will be certain lag of time. So when you build a system, you have to understand the kind of the time
либо целиком на серверах организации.
that is needed for communication between the nodes. Talking practically, if you have an organization, a company, and you understand which lags firewall will introduce, right? Then, of course, you develop the system, give it all that. It's better to do it on site, but kind of
Спасибо.
if you decide to do it in the cloud, do it in the cloud. But it's better to have it in one place rather than two places. Another question. Yes, question about the ownership cost. Since you have everything on board, including the streaming service, you hide this difficulty from your clients. But the system is difficult. There is a large number of things which will be in coercion. The difficulty doesn't go away, and I'd like to see what you think about that. Any system, even the simplest system can go wrong. You know, Murphy law tells us this. This is an axiom. I don't think that we have to argue about that. You're right, though. The system is difficult. We hide this difficulty from our customers. However, the initial code is open. Talking practically, right? Because I think you were hinting about the empirical experience. No. What I want to get down to is who is going to repair if anything goes wrong. Well, it depends where it happens. On PM, already today we have a large number of installations that have been installed autonomously without our support. So I think there will be no difficulty in installing the system. Companies are big, but the specific people who are in charge of operating a specific program are really small. And I know that it works in practice. In order to do it easier,
по эксплуатации.
we did COS.
Большое количество вопросов скрывает. Если
We published it.
приходите, ответим.
I think there are a lot of questions that are answered there. And if you have more, please come to us and we'll have support.
Способности бизнеса.
If you're interested with interruptibility of business operations that is based on your databases, yes, come to us, we will support you. Thank you. Okay, a question on the other side of the room. I'm from the Voskhod group. Thank you for your presentation. Quite impressed. I have a question which is down to earth compared to my colleagues' questions. During streaming, the logs are delivered in packages rather. When you normalize messages from that streaming, how do you work with an error? Let's say in a package, there are 1,000 different bad messages. Let's say 3 of them contain mistakes. What do you do with that? Do you sift for all 1,000? Well, there are different options, and this is not our solution. This is the systemic solution. The first option, if you find an error, stop. The maintenance guy will come to you and will take care of that. The second, throw away the errors to continue working. And the dead letter queue is the third one. So right now we pass the error messages because we have normalization systems that we trust. Why do we do that? Because as we found out, it's very hard in a big flow of data to find which messages have errors. SQL is not good at that. So we go to DL code. We understand that it's important. Well, we're planning to do it as the next step. And another question. Thank you for your presentation. It was very interesting. I have a question about federated queries. From the security point of view, when database sends a query to database, it's not always good. You use federated queries, or maybe there are some other means of communications between YDB and other DBMSs. What can increase the security level? Yes, again, you're right. Some time ago, inside the Parquet, we found a critical vulnerability that could attack the system that works with these files. We have the database with federated queries, and we have 2 options of working with outside data. The first is when YADB, its code, goes outside, gets the data, and starts working with them. And the second is when we have an outside server on the side, and it sends us the data. When we work with object storage, we go there with C++ code, because usually the object storage stores terabytes of data, and we cherish the possibility to process this efficiently. Other than that, indeed,
но у нас есть миллион различных процедур сертификации, аудита, сек-аудита, пентестов, которые все это проверяют. Но действительно уязвимости нулевого дня бывают, и на нас они тоже влияют.
То есть вот эта вторая история, которую вы сказали, это вот что-то типа шины данных, да?
Нет, второй гошный компонент или что?
Ну, то есть вот альтернатива прямым запросам.
Нет, это не шина данных.
Это внешние коннекторы.
Это внешний компонент, мы его специально, то есть это внешний компонент, он написан на Go, у него есть интерфейс взаимодействия между самой базой данных и им. База данных ему дает команду: сходи туда-то, посчитай результаты, верни мне. И вот этот коннектор в этом случае выступает таким промежуточным звеном. Если что-то пойдет не так, то саму базу это не затронет, повлияет только на этот сервис.
То есть
просто
коннектор на отдельном сервере установлен, да?
Просто для построения коннекторов используются два подхода. Есть внутренние коннекторы и внешние. Мы используем, практикуем оба. То есть есть внутренние и внешние коннекторы.
Спасибо.
И еще один вопрос успеваем.
Добрый день, спасибо. У меня близкий вопрос. Есть ли ролевая модель, как она устроена, как мапится для сервисов и для пользователей, и как мапится от таблиц роль, привилегии на колоночные, и при хождении в другие сервисы, в другие хранилища при федеративных запросах?
Ролевая модель есть. То есть у нас есть группы пользователей, права достаточно гранулярные. Прав на ячейки пока нет. То есть то, что входит в понятие fine-grained access control, это в каких-то будущих релизах появится. Пока что права ограничиваются более верхнеуровневым объектом, это или таблица, или...
The rights are given for the object of a higher level directory.
Права могут быть очень гранулярными.
The rights can be very granular,
Обновление,
all up to reading, renewal, deleting of a string. So, stemming from this model, you can put together the groups with different role users.
Который как-то обрабатывает данные,
If there is a topic that
можно ли в этом топике навесить дополнительные ограничения?
processes data and
Пока нет.
stores it for analysts, can you put additional limitations to that topic? No, not at the moment.
На ваш взгляд.
Okay, thank you very much. Now, the traditional part of our conference, the best question.
Мне кажется, там, где мы затронули федеративные запросы, внешние и внутренние.
Давай его.
I think the question about federated queries. I have a different opinion, but okay.
К федеративным источникам данных.
I will go with my choice. It's the federated queries question. Security of federated queries.
Спасибо за вопрос.
Please come up. Thank you very much for your
Спасибо, ребята.
smart question.
Интересно.
Guys, thank you for the presentation. It was very interesting.
Следующий доклад.
Don't go too far away. We'll have the next presentation in 4 minutes.